All right, hi, this is Andrew Bunnell again, and now we're going to look at processing the data from projectile kinematics. So I had the image of the ball, and I imported the data into this worksheet right here. Now I'm going to use Excel just because I have a worksheet set up that I can quickly and easily manipulate the data. This is what they use for the simulation version, and I'm going to talk about a little bit about the uncertainty. And so quickly, this page right here just has the delta time, and then it has the time versus the position, and then the derivative of position versus time, and then the derivative of velocity versus time, and the same thing in the wire, which is really the z-axis. I'm using a 39.8 hertz photo because that's what it said on my picture. I set it to 40 and the projector changed just a little bit. I'll show you in a minute what happens if you change that on the final slide. Also, I have this steel ball measured at 62.1 grams, plus or minus 0.1. Your first image should look, and then I have all these worksheets set to auto-update to that page. Your first image should have an X and Y. I didn't put in the title or the axis titles or units. For final product, obviously, I need to do that. And you can look at this and say, yes, it's a projectile. Residuals look pretty random. Here's my values. This one was really just to check to see if everything's in line. Now, when you parameterize x versus t, you expect a nice linear line, but I want to show you something really quick. If you look at these residuals down here, they're nice and flat when the coefficient of x squared is not set to 0. But if I fix that to 0 and click Perform Regression, look at what the residuals look like. It looks just like the photograph. It looks like a nice arc, and there's some parallax from the camera not being able to see perfectly straight. I position the camera right here in the middle, and down here and down here and up here, there's a little bit of parallax. So if I don't, even though I think it's linear, if I uncheck that and click Perform Regression, look at my, it suggests I have an acceleration value of negative 0.08, and then it's all perfectly flat from that rounded shape. And I'll take that number here in a little bit. Okay, so next I'm going to go to the velocity and look at the velocity, and if I uncheck that, I get a really, really small slope into 0, and so if I check it, now I get a slight curve, but it's all within, that one's not quite within 0, this one's within 0, so that's the standard error. And let me fix those two and check it again, and now there's my velocity, my standard error of my velocity, and I'm pretty sure it's a nice flat line. Now my error bars, as you've noticed, have gotten bigger and bigger. And here is an example of, well, now I'm getting a value for A2. I should be able to fit a line that's flat, but I get a value, when I uncheck it, I get a value that's close to 0, but it's not quite 0. But I could also say in the same regard, hey, there's a slight curve to that line, but it's well within 0. And so I could technically fix the first coefficient and fix the second coefficient to 0 and basically just fit a single line with no slope and perform regression. And there we go. We get a nice flat line, really, within error, because when you take the second derivative, the error bars blow up and they get really big. Okay, now let's look at z of t. Now in z of t, it's not quite as obvious because you expect the ball to travel in an arc anyways. And this is time versus position in z. And now if you notice this number right here using the formula, you'd expect, this would tell you gravity is 10.06. But if you remember back to my xz says because of that arc, because of that xt, because of that arc in the data, when I perform a flat regression, see that little arc right there, I need to uncheck that, and I'll add that little arc. I get an extra 0.08. When I go back over here, if you take 5.03 and minus 0.08, you get 4.95, and that's much closer to 9.80 than it's 9.90 versus 9.80. So that's one good possible source of error. You can't see the residuals because it just adds that curvature from the picture right on into the formula. Now, when going to velocity in the z direction, once again, I have a value that's a little bit too big, and my residuals look scattered, and if I uncheck that, they still look scattered, and it's all within 0. And 10.8, I'm not quite 9.8, but I believe that's because of that curving we just saw. And then let me show you one more error. Once again, the uncertainty error bars got really big for this AZ, and taking the second derivative with respect to time, and that's the average second derivative, we get 9.87 and a really big standard error because the error bars are really big. Alright, so now, as I mentioned before, there might be a little bit of an error based on what the flash was set to. And so what I just did is I copied this value down here and typed in the flash was set to that. But let's go take a look to see if the flash was just a couple tenths off. And to do that, I'm just going to come over here and let's say I change it to 39.6, 2 tenths of a second, or sorry, 2 tenths of a hertz different. Now I'm going to copy these values right here, which is my acceleration data, back over onto my acceleration page right here. Now, looking at my data, my standard deviation, my residuals changed just a little bit, so I'm going to change those values and copy them down. I'm going to click on here and fix error bars. They changed just slightly. And now, by changing just 2 tenths of a hertz difference, or 2 tenths of a hertz difference, that changes my value for gravity or expected acceleration by 0.1 meters per second squared. It still falls well within my standard error, but if for some reason the little sensor on the back of that device wasn't reading correctly, it could be off by a tenth of a second, or sorry, 0.1 meters per second squared. Another thing, aside from what we looked at, right, wrong one, uncheck that. Okay, let's go back to here, this one right here. Now remember how we had that arc from trying to fit a flat line and there was a slight amount like that. Also, if the picture itself, if the fit calibration window isn't done correctly, that can also be a source of error. For example, if I measure a vertical distance of 0.61, but in fact it's 0.61 meters, but in fact it's 0.62 meters, that's going to make a big difference on my acceleration due to gravity with my fit calibration from imageJ. And that's it for today. Thanks for watching.